Okay, so we just saw a problem about two roofers. We had an experienced roofer and a beginning roofer, didn't we? And they told us that the experienced roofer can roof a house in 54 hours, whereas the beginning roofer needed 81 hours to actually do the exact same job, right? And then they're asking us, well, if these guys work together, how long is it going to take them to actually roof that same house? So here's the deal. I call this problem a work principle problem. And you're like, why do you call it that? Well, because I got people working together. Okay? I have people working together. And I've got a roofer, don't I? And I have an experienced roofer. I have a beginning roofer. And then I got these two working together, don't I? Okay. Now, they told us the hours that they took when they worked alone, didn't they? The experienced roofer took 54 hours working alone. The beginning roofer took 81 hours working alone, right? And then working together, I don't know how long they take working together. I'm going to call it T. Now, let me ask you something. When people work together, right, if they're working together to get a job done, do they take more time working together to get it done, or do they take less time working together? Yeah, they take less time, right? Unless you're washing a car and you end up with a water fight, it takes less time when people work together, right? Okay. And when people work together, it's out of which of the four operations do you think it might be when people work together? Do you think that calls for an addition problem, a subtraction problem, a multiplication, or a division problem? Which one do you think it calls for? Yeah, it calls for an addition problem. So technically then, if I added these two roofers together, it should equal how much time it spent working together, right? Well, if I take 54 and add it to 81, that's going to give me way more than it should take. Here's the deal. I can't add their hours because their hours are different. 54 hours for the one guy, 81 hours for the other guy. T hours where I don't even know what the T stands for. These are three different time references. And this is the work principle problem. So don't write, just listen, and then go back and play it again, and then write down. So the real deal is this. I need to figure out the amount of work done in 1 hour. And I say 1 hour because we're talking about hours. If they talked minutes, I would talk 1 minute. Got it? Okay, so think about it. This roofer takes 54 hours to do the job. So in 1 hour, how much of the job does he actually complete in 1 hour? Yeah, he completes 1/54 of the job in a single hour. And in 2 hours, he would complete 2 out of 54 parts of the job, right? And then 3 out of 54 and 4 out of 54. Does that make sense? Okay. Now, this beginning roofer takes 81 hours to do the same job. So in that single hour, how much does he get done? Yeah, he gets 1/81st of the job done in the exact same hour that it took the experienced roofer. The experienced roofer gets a 1/54th done, and the beginning roofer gets 1 out of 81 done, both in the exact same hour. Are you with me? So if they work together, yeah, that's 1 out of T hours. That's how much they get done. Working together, this is how much they'll get done in that single hour. This right here is the basis of the work principle problem. How much do they get done in the same time reference? I could have said in the first 2 hours versus the first hour. With me? It doesn't matter. But let's just keep it very basic. In 1 hour, not 2, not 3, not 10, in 1 hour, this is how much each of them get done in the same hour. So, now I can do the adding, and I know what it would equal. In 1 hour, I'm going to add that 1/54th, and I'm going to add that 1 over 81, and it's going to give me that 1 over t. These are each of the amount of work done in that single hour. These two amount of work in that 1 hour equals how much gets done together in that 1 hour. Cool? Okay. So, another equation with fractions. What are we going to do? Yeah, we're going to get rid of them. So hopefully you follow along. Get the common denominator, right? Hopefully you follow along with what my next line is going to look like. I am going to, after I get rid of all the denominators, I am going to end up with this equation. Hopefully you followed along with that. I can hear some of you already. No, I didn't. What'd you do? I multiplied these are this is my common denominator, multiplying all three of these together. And I multiplied it by each fraction. And this is what I ended up with. Cool? Okay. And now I got a nice little equation to go solve, don't I? All right. So when I solve, I'm going to add the 81 and the 54. So what do we get? 135t. And then I need to multiply the 54 and the 81. I know you got your calculators out. What's 54 times 81? Good. I think you got the same thing I did. 4,374. And when you do your division, that's 32.4 equaling t, isn't it? Now, t was the amount of time, right, when they worked together. And that time was in hours. So this is 32.4 hours. So when they work together, they take 32.4 hours to roof that house. Now, interestingly enough, this time is less than the experienced guy at 54 hours, isn't it? Does it make sense? If this experienced guy has help, shouldn't it take less than the 54 hours to actually roof this house? Yeah, it should. Assuming his helper is capable, yeah, it should, right? Okay, makes sense? Hang in there. Got another one of these. Okay, so we just read a story about two hoses filling up a goldfish pond, right? They told us that one hose could fill up the goldfish pond in 36 minutes. And then they said two hoses can fill that exact same pond in 20 minutes. And they want to know, well, how long does it take a second hose to fill the pond if that's the only hose filling the pond? With me? Okay, so here's the deal. What kind of problem do you think this is? Yeah, it's a work principle problem again. Why? Because I have two hoses working together. Are you with me? It doesn't just have to be people, it could be machinery. Because a manufacturing facility has more than one machine making parts or making whatever product it is, right? So, understand that. It's more than just people for a work principle problem. So, we've got two hoses in this case. We got the first hose, right? We have the second hose. And then we have them working together. Now, alone. And that alone was in minutes, wasn't it? How long did it take the first hose working by itself? If that was the only hose that was turned on, yeah, it took it 36 minutes, right? Now, do I know how long it took the second hose? And if you said 20 minutes, that's not correct, because reread the problem. It said 2 hoses can fill the same pond in 20 minutes. So does the 20 minutes refer just to the second hose, or does it refer to them working together? Yeah, the 20 minutes is them working together. And their question was, find out how long it takes the second hose alone to fill the pond. And I don't know that, so I'm calling it S. Cool? Okay. Remember, working together is what operation? It's addition. So I would add the first and second hose together, and that would equal whatever together, right? But, yeah, 36 plus S equaling 20, I'm going to get a negative answer. Hoses don't work backwards. I mean, time doesn't work backwards, right? We don't have a time machine. It doesn't go backwards. So remember, the key is the amount of work done in in this case, it's 1 minute, because the reference is in minutes. So if it takes 36 minutes for the first hose to fill the pond, how much of the job does the hose do, or how much of the pond gets filled in that 1 minute by the first hose? Yeah, 1/36 of the pond gets filled. What about the second hose? I don't know how much gets filled. What about when they work together? Yeah, 1/20 of the pond gets filled in that minute's time. With me? Okay. And now I can do the addition. Now I can take 1/36, add the 1/s to it, and it'll give me the 1/20. Cool? All right. Yep. I'm seeing 3 fractions. Do we want to keep them? Nope, let's get rid of them. So, I am going to take all 3 of these denominators and I'm going to multiply them by those fractions. Why? Because I want to get rid of it. I'm finding the common denominator and I'm getting rid of those denominators because I don't want to keep them. So let's see if you agree. Those 36's will cancel. So I'll have 20s, right? The s's cancel here, so I get 36 times 20. And then the 20 cancels, and I get 36s. Good? Okay. I need my s's on the same side. So what will that give me? 16s? All right, what's 36 times 20? I know I got those calculators. Good, 720 equals 16s. And then, yep, divide both sides by 16. I don't know, does it go in evenly? Did you get it? I got it. Yay, it goes in evenly. I got 45 equals S. Did you get that same answer? Okay, go back. S stood for the second hose. How long it took the second hose working alone. And so that 45 is in minutes. So if they just put the second hose in the pond and turned it on, it would take 45 minutes for that hose by itself to fill up the pool. I don't know, maybe it's a smaller diameter hose. Maybe that's why it takes longer. Does this make sense? Hang in there. Got another story for us. Okay, so we just looked at a train problem, right? They told us about 2 trains, train A and B. They were heading in opposite directions. They left at the same time and headed in opposite directions, correct? They said that train B travels 10 miles per hour faster than train A. And in 7 hours, the trains are 910 miles apart, right? And so they want you to tell them how fast each train was going. So here's the thing. There's 3 components that they spoke about in this particular story. They talked about the fact that the trains left at the same time. They also said something about the distance between each train. And then they also asked you how fast they were going. They wanted their speed, right? And in another problem, speed is another word for rate. They're kind of interchangeable. So here's the thing. This particular story requires a very specific formula. And the formula is written as distance equals rate, which is another word for speed, multiplied by time. You may have seen it written as D equals R times T. Got it? Okay, so when I read a story like this that involves these three components, I literally write out my formula at the top because I need to start filling in the pieces of information that they've given me so I know what it is I'm looking for. Does that make sense? Okay, so first things first, when I know I have a distance problem, I write the formula down. Second thing I do is I'm like, well, what are they talking about? In this case, they're talking about two trains. They labeled them train A and train B, didn't they? Okay, so then off here to the side, I'm going to write train A and train B. Good? Okay, so let's start at the beginning and see what it tells us. They said two trains going in opposite directions leave at the same time. So let me ask you something. If they leave at the same time, that means they're probably traveling the same amount of time. Don't you think? Okay. Did they tell us? Well, let me leave it there. Okay? I'll just stop right there. I'm getting ahead of myself. We good? Okay. And by the way, for us visual people, I have two trains leaving at the same time. Right? We have train A and train B. And they both left the station in opposite directions. Good? All right. So let's see what else it tells us. Let's look at the second sentence. The second sentence starts at train B travels 10 miles per hour faster than train A. Right? So who's going faster? Train B is going faster. By how much? Yeah, by 10. So that means that you're going to do what operation if it's going faster by 10? Yeah, you're going to add. So here's the deal. Under speed, which is rate, you know to train B you're going to add 10. The question is, what are you going to add 10 to? Good, I heard some of you. You're going to add 10 to the speed of train A. Well, do you know how fast train A is going? No. All right, so I'm going to call it R for rate, or A for train A, or S for speed, whatever. I'm just not going to use X. And train B then is going to be train A's speed plus 10. Does that make sense? Okay, got it. Now, the next part says in 7 hours. So I'm stopping there. So here's the deal, right? Train A and train B, they left at the same time, didn't they? And now they're saying 7 hours later. So question, how long, right? What amount of time did train B travel for? Good, 7 hours. And train A, how long did train A travel for? 7 hours also, because they left at the same time and now it is 7 hours later. Are you with me? So train A traveled for 7 hours and so did train B. They both traveled for the same amount of time. Does that make sense? Okay. And now they're telling us, after we know they've traveled for 7 hours, that these two trains are 910 miles apart. So where train A and train B ended, we know that this is supposed to be 910 miles, right? So the 910 miles is a distance, isn't it? Is it the distance for just one of these trains or both of them? Yeah, both of them. So this is 910 miles. Good? Okay, looks like I have all the pieces to my puzzle here, don't I? Okay, one thing to verify. This distance was in miles, wasn't it? This rate was in miles per hour, and they gave us the time in hours. We have to make sure these units are matching up. With me? Distance is in miles, time is in hours, rate better be in miles per hour. Cool? Because if it's not, if they gave me like this in feet and this in miles, I'm going to have to convert. Gratefully they didn't do that. Yay. Okay. Now, I'm going to use a word here that's going to help us. This 910 miles is the distance between the two trains, right? Couldn't you think of this as the total distance, right? By the time these two trains ended, that's the total distance. So let's talk before we start writing numbers. So the total distance, right? The total distance is going to be equal to us knowing what? Yes, this total distance is going to be equal to us knowing the distance of train A and the distance that train B traveled and doing what between them? Yes, adding them. If I add the distance that train A traveled and I add the distance that train B traveled, that will give me this total distance, won't it? Do you agree? Okay, so let's look. What's my total distance? 910. How do I find distance again? Yeah, the formula is distance is found by taking the rate or the speed and multiplying by the time, correct? Well, then to find the distance of train A, I'm going to take the speed of train A and multiply it by the time it traveled. So that's going to be 7r, isn't it? Plus the distance of train B. Again, distance I find by taking the speed times multiplied by the time. The rate multiplied by the time, which means I'm going to take this 7 and multiply by r plus 10, aren't I? Does that make sense? Okay, well, now I have a nice little equation to go solve, don't I? All right, so I have 910 equals 7r plus 7r plus, good, 70. So we have 14r there, don't we? Plus the 70. And what are you going to do? Yeah, subtract that over. What do we get? 840 equals 14r. And divide by 14. Okay, I know you guys have your calculators out. What'd you get? Yep, 60. I heard you. Does that make sense? Okay, so R. What did R stand for? R by itself stood for the rate of train A. So train A is traveling at 60 miles per hour. That means train B is traveling at 70 miles per hour. Does this make sense? Okay, then hang in there. Got another one of these for us. Okay, so we just looked at another problem, and it said that a person drove 140 miles in the same time that it took a plane to travel 520 miles. The speed of the plane was 190 miles per hour faster than the speed of the car. They want us to find the speed of the plane. So tell me, what kind of problem do we have here? Good. It talked about the three components, didn't it? It spoke about the amount of miles driven, which can be called distance. It spoke about the fact that they drove this, or it was in the same amount of time, right? So there's time. And then they talked about the speed. So here's the deal. That means this has distance, rate, and time. So what kind of problem is this? It's a distance problem. So what's the first thing I should write up here? I should write the distance formula. So distance is equal to the rate or speed multiplied by the time. And the last problem talked about train A and train B. In this case, what are they talking about? Yeah, they're talking about a car and an airplane, right? So car and a plane. All right, so now that we have this, let's go back and pick out the information that they've given us. They said that a person drove 140 miles in the same amount of time it took a plane to fly or travel 520 miles. So any information in that sentence? Good. They gave me a distance, didn't they? So they told me the car traveled 140 miles. So distance is in miles here. And the plane, 520 miles. So gratefully they're both in miles. Otherwise I have to convert. And they actually gave me one other key piece of information. They said the same amount of time, didn't they? Now here's my question to you. Later in the story, did they say anything about how long each of these vehicles traveled for? No, they didn't. Which means I don't know how long each vehicle traveled for. So, do I know how long the car drove for? No, I'm going to just call it T. Do I know how long the plane flew for? No. But since they said the same amount of time, then I'm going to call it T also. Are you with me? They said same amount of time. They may not have told me the amount of time, but since they said the same amount of time, that means I'm going to call them both the same variable. Cool? Okay, everything taken care of in that first sentence, right? Let's look at the next one. The speed of the plane was 190 miles per hour faster than the speed of the car. Yeah, so the plane is faster, which means you're going to use what operation? Good, you're going to add. You're going to add how much? Good, you're going to add 190 miles per hour, right? What are you adding to 190 to? Yeah, the speed of the car. Do you know how fast the car is going? No? Okay, what do you want to call it? Okay, R for rate, that's fine. No X's. C for car, S for speed, great. Which means here the plane is going to be the car's speed plus 190 miles per hour. Agreed? Oh, by the way, since the rate is in miles per hour, what do you think the time is in? Yes, the time is in hours. Good. And then they said, find the speed of the plane. All right, no problem. So here's the deal. How many variables did they give us? 2. T and R. I have 2 variables in this problem, which means I'm going to need how many equations? 2. One equation is going to be for the car. The other one is going to be for the plane. With me? Because the equation says distance equals rate times time. So one equation represents the car, the other equation represents the plane. Because they have their own separate distances. The last problem, the train problem, the distance between the 2 trains were combined. That's why we had one equation, because we only had one variable. In this problem, they're different. They're separated. Cool? Okay, so What's the equation for the car? Good. 140 equals r times t. What's the equation for the plane? Yeah, the equation for the plane is going to be 520 equals r plus 190 times t. Are you with me? And you're like, where do I go from here? Well, you can use your substitution or elimination methods, which means you need to solve for one variable, plug it into the other, or something of the sort, right? Okay. Now, do me a favor, don't write, just watch a second. There's one piece of information they told me here in this problem which is actually going to help us. The fact that the times were the same tells me that I need to get the t in each of these equations by itself. The fact that the time was the same tells me to get the t in each equation by itself. Isolate the t in each equation. Watch. So over here when I get t by itself, it would be 140 divided by r, wouldn't it? That's the time for the car. Remember, this is the car over here. When I get t by itself over here, that would be 520 over r plus 190, right? This is the time for the plane. This represents the time for the car. This represents the time for the plane. We were told that they travel the same amount of time, which means the time for the car and the time for the plane need to be good, the same. Give me another word for the same in math. Equal. I heard y'all, which means the time for the car must equal the time for the plane. The time that each one of these traveled must be equal to each other. Does that make sense? Awesome. Okay, and now it becomes like we've done before. We want to cancel these denominators, so we multiply both sides by the common denominator and wipe out each denominator, right? Okay, so when we do this, whoops, that's an r plus 190. Sorry about that, y'all. That's what happens when we bring things a little too fast. So the r plus 190 cancels on this side. The r cancels on that side. So what do we got? We got 140 times r plus 190 is equal to 520 times r, right? Okay, so do our distribution. Okay, I admit it, I gotta get my calculator out. So I have got 140 times 190. So hopefully we have the same. I have 26,600 when I multiply the two of those together. Did you get that also? Now what? Good. Move the 140 to the other side. So I'm going to put it over here because I'm running out of board space there. So I have 2,600 is equal to, 380r, correct? And lastly, we get to divide by that 380. So what'd you get? 70? Good. I got the same thing. All right. What did R stand for? The R by itself. Yeah, it stood for the speed of the car, didn't it? So the speed of the car was 70 miles per hour. So that means the speed of the plane is, good, 260 miles per hour. Good? Does that make sense? Awesome. Hang in there. Got one more of these for us. All right, let's take a look at this last problem. In this last problem, they were talking about a boat traveling upstream and downstream, right? Okay. So when you read it through, did you get an idea of what kind of problem this was? Yes, it's a distance problem, right? Because they talked about a distance, they talked about time, they talked about how fast it was going, correct? All right, so what's the first thing I should write down here? Yeah, I should write down the formula. So, distance equals rate multiplied by time. And what are we talking about here? We're talking about a boat, and the boat's traveling upstream and downstream, right? Okay, so let's see. The boat going downstream, because they said downstream first, so I'm writing downstream first. And then they talk about the boat traveling upstream. All right, so let's go back and reread each sentence, shall we? And let's see what information we can get out of it. So, they said the speed of the river's current is 4 miles per hour. Okay, they said the speed of the river, but this distance problem is talking about a boat going up and downstream. All right, so here's what I'm going to do. I'm going to keep that off to the side. I might need it, I might not need it. I don't know yet. So, over here, I'm just going to say speed of river, right, is 4 miles per hour. I'm going to leave that in its own little box. I may need it. We'll see. And then they said, if the boat travels 17 miles downstream, in the same time that it takes to travel 9 miles upstream. And then there's a comma, so I'm pausing, because a comma means pause, right? Okay, so the boat is traveling 17 miles downstream in the same time it takes to travel 9 miles upstream. So that's representing the distance, which is in miles. So it said 17 miles downstream, 9 miles upstream, but remember the phrasing? They said in the same time. And they didn't tell me anything about time later. So I know those variables are going to be the same, aren't they? Just like they were in the last problem. Does this make sense? Okay. And then they said find the speed of the boat in still water. Well, that's an interesting question. So let me ask you something. Do I know how fast the boat is traveling right now? Just the boat. No, it didn't tell me anything about how fast the boat was traveling. So I'm going to sidetrack us over here a second. All right. So let's see. Speed of boat. Do you know it? Neither do I. So I'm going to call it R, miles per hour. And you're like, wait, why is that off to the side? Because they said in still water. So in still water means the water isn't moving, right? It's not moving. When you're going downstream, the water's moving. When you're going upstream, the water's moving, right? Okay. So I'm going to sidetrack you a second. Here's how I'm going to get you to understand something. So remember when you were a little kid riding your bike and the wind was blowing and you had the wind coming from behind you, right? So the wind was coming at your back, you're traveling this direction and the wind comes behind you. The wind's pushing you, isn't it? It's helping you go faster, isn't it? Right? So however fast you're pedaling, you could add the speed of the wind, and that's how fast you'd really be going, right? Okay. Imagine this boat going downstream. Zing! So the boat has its own speed, right? But since it's going downstream, the river's also pushing it, isn't it? So whatever speed the boat is going, I can add that speed of that river because that river is pushing it even faster, isn't it? Just like when you were pedaling your bike and the tailwind came, it pushed you even faster, didn't it? So, I know the speed of the boat is R, but because it's going downstream, it's getting some help, isn't it? Yeah, it's getting 4 miles per hour help, isn't it? So we add 4 miles per hour to it, don't we? And yes, this is miles per hour, which means over here is just hours, isn't it? Does that make sense on the downstream? Okay. Now, pretend you're riding your bike again. And this time the wind's coming against your face. It's basically pushing you back, isn't it? So now let's think about this. You're pedaling, but the wind is pushing you back. So is it helping you go faster, or is it making you go slower? Slower, because now the wind's pushing against you, so you're going slower, right? Let's think about this boat. This boat's traveling upstream now. This boat is traveling however fast, but now the stream is coming against it, isn't it? The stream is the stream helping it go faster, or is it making it go slower? It's making it go slower. So the boat's got its own speed, but now it's going slower. It's going slower by 4 miles an hour, which means now I'm going to subtract 4 miles per hour from the speed of that boat, because now that boat is slowing down a little bit. Does that make sense? Awesome. And if it doesn't, pause it, rewind, listen to it again. Cool? Okay. So, do you notice I got 2 variables again? Just like the last problem? Right? And there's 2 separate distances. 2 separate distances, 2 variables. How many equations? Yep, 2 equations. One is going to represent the boat going downstream. And the other one is going to represent the boat going upstream. Remember the times are the same? Do you remember what that did for us in the last problem? Yeah, I got to solve for t in both of these equations, don't I? Because when I get t by itself, that means these times should be equal to each other, shouldn't they? Because this now is the time that the boat takes to go downstream, and this is the time it takes the boat to go upstream, and they're supposed to be the same. So what am I going to do? Yep, I am going to set them equal to each other. So when I set them equal to each other, now I'm sorry. Did you guys catch me? Some of you did. Some of you are trying to yell through your computer screen, stop! Yep, I blew it right there, didn't I? I got stuck on the number 17. I'm so sorry, you guys. See, as I said, this is why I need you doing this stuff with me. The boat going downstream is 9 equals, right? And then I'm taking 9 divided by r minus 4, right? And, right? I am so sorry. But I'm grateful you guys yelled loud enough that I could hear you. Yay! We good? Do I have it set up now? Downstream is 17 equals this. Upstream is 9 equals these 2 multiplied together. And I solved, okay, and we set them equal, okay. Got it. All right. And now we get to multiply both sides by the common denominator, right? Which is the r plus 4 times r minus 4. And yes, I know, some of you already see the next step. That's great. Some of you need to do what I'm doing here so you can see it a little bit clearer. And I end up with this equation once the fractions are gone, right? Okay, I'm going to come up over here because I'm running out of board space. So we have 17r minus 68, right? Equals 9r plus 36. I'm going to bring the r's to this side. So I have 8r. And some of you can do the double move at the same step, and some of you should do it separately. You know who you are, so I add that over, right? So what is that, 104? Divide both sides by r, and I got 13. Did you get 13? Good. So, r R was the speed of the boat, wasn't it? R is just the speed of the boat itself with no water moving. So, over here, the speed of the boat with no water moving, 13 miles per hour in still water. That's how fast the boat is going without the water moving. When the water is moving, the speed of the boat is going to change. But when there's no water moving, it's 13 miles per hour. We good? Again, I would suggest rewinding any part of this you need to, playing it over again, making those notes to yourself so you know how to handle any homework you've got to do. In the meantime, you guys have fun with this stuff, and I'll catch you on the flip side.